think you do with that value? It would be another distance. So what would be the unit of moment of inertia? Kilogram meter squared. What do you think this one would be? Foot to the fourth, right? To the fourth, and meters to the fourth. So the terminology is really, I think it's important, so that when you talk about this to someone, you actually know what it is. Okay, so I would like you to make sure that you're writing all this down. Okay?
How are we finding a second moment of?
I'll show you. All the equations have been derived for us already, so we're going to do it all with tables. And if we had all Excel set up, if we turned on all the computers and did Excel, we could do it a lot quicker. JJ?
Those units don't make sense.
I know. They don't, because we already know that a moment is a force times a distance, right? But now we're learning that term moment is used to describe other things. Moment of mass, moment of area, moment of volume, and the units do look really weird.
So is this distributed area or distribution?
Distribution, sorry, distribution. Distribution of area, sorry. Make sure you keep all your notes. These notes are really important for dynamics and strength of materials. A lot of times teachers just do the problems and don't necessarily tell you what's going on. I'll give you an example in a minute so it kind of makes sense. I just want to make sure everybody's writing stuff down. Oh, okay. Oh, let me give an example. Maybe we'll go there now. Okay, is everyone ready? So, I have a mass, right? My body has a mass. And let's say I'm talking about my moment of mass, moment of inertia, from where Haley is. So you're looking at where Haley is located, and you're trying to figure out what my moment of inertia is, versus the corner of the room. If your reference point was Haley versus the corner of the room, to my moment of mass, where would I have a greater moment of inertia? Measured from where Haley is or measured from where the corner is? The corner, why? It's further away. So maybe the units still don't make sense, but if we're looking at, if we look at area, we were looking at foot cubed, right? The further away something is, the larger the value it's going to be. So let's look at an example in mechanical engineering. Think of a bicycle wheel. So we're probably, most of us, or maybe all of us, are thinking about a traditional bicycle wheel, right? Where there's the metal around the outside and then there are all these spokes. Where is most of the mass distributed? Where is most of the mass in a wheel? Well, not the center. That's not where the mass is. Maybe that's where the moment of inertia is greatest.
The wheel?
The rim. Right around the rim, right? That's where all the metal is. And maybe they used aluminum later on, it's lighter, but still, the spokes, in comparison, the spokes are very light. They have less mass than out here. So we're looking at, when we look at a bicycle wheel, we're looking at the distribution of its mass. On a traditional bicycle wheel, it's heavily loaded with mass on the outside. And then the spokes are not that much mass. So now let's think of a non-traditional, a more new bicycle wheel. You've seen the ones that are discs. They So now, what did they do with the mass? They distributed it more evenly.